This video is on least squares regression. What is that? Well, let's start with this example. I have a scatter plot here. We know what a scatter plot is. So I've got 15 dots in the scatter plot representing a sample of 15 high schoolers from across the United States. I have their foot length measured in centimeters and their height measured in centimeters. Notice we're using foot length as the explanatory variable and height as the response variable. Is there a relationship between the length of the foot and the height of the person? If we knew a person's foot length, would that help us to understand what their height might be? So let's analyze that question. We know how to find correlation. The correlation between the foot length and the height for the students in this sample of 15 kids is 0.689. But we want to go one step further. How do we fit a linear model to this data? How do we determine a line of best fit to fit these points in a way that it could be used as a model for the set of 15 points? In order to understand the line of best fit, we have to understand a concept called a residual. Residual is the actual value minus the predicted value. The residual is the vertical distance on the graph from the actual point to the point on the line for that same x value. That vertical difference between the prediction and the actual point. It tells us how far off the model's prediction is from reality for that x value. So for a particular foot length, the model will predict some height. The actual height for that person with that foot length might be something else. And what is that difference? Obviously, we don't want that difference to be very big. We want small residuals overall. So let's consider this line. This line on this scatter plot is the line of best fit because it is called the least squares regression line. It is the line that minimizes the sum of the squared residuals. So we're not just minimizing the residuals. That's not our goal. Our goal is actually to minimize the sum of the squared residuals. Why squared? Because some of the residuals are positive numbers if the actual value is above the predicted value, and some of the residuals are negative numbers if the actual value is below the predicted value, if the point is below the line. And if we just added them up, the positives and negatives would cancel each other out, and it wouldn't be very helpful. We could take the absolute value, but in statistics, the preferred method of making things positive is to square them. Just like when we were calculating the variance, we squared the difference between the number and the mean. So that is our goal in creating the line of best fit, is to minimize the sum of the squared residuals. So if I were to draw all of the residuals from each of these points to the line, each of these vertical segments connecting the points to the line, I want the squared values of those distances added together to be as small as possible. How do we calculate that least squares regression line? Well, it's a line. And if we remember from algebra, to write the equation of a line, we need two things, a point and a slope. The slope of the least squares regression line is equal to r times the standard deviation of y divided by the standard deviation of x. R, the correlation, times the standard deviation of y divided by the standard deviation of x. So if the correlation is positive, the slope will be positive. If the correlation is negative, the slope will be negative, which makes sense. If our points generally have a positive association, we want the line that goes through them to have a positive slope. Same with negative. And notice the y goes on the top and the x goes on the bottom, just like the old formula from algebra for calculating a slope, y2 minus y1 over x2 minus x1. The y's always go on the top, the x's go on the bottom. The point that we need for the least squares regression line is x bar, comma, y bar. The mean of the x values as the x coordinate and the mean of the y values as the y coordinate. That point will always be on the line. If you want to know why, you just need to look in your book at page page 173-ish, and it explains why. So let's find the equation of this line that I claim is the least squares regression line for these 15 points. We've got R, that was 0.689. I've got the mean of the foot length, I've got the mean of the heights, I've got the standard deviation of the foot length, and the standard deviation of the heights. So we should be able to calculate the slope, which is R, times the standard deviation of Y divided by the standard deviation of X. So that is 0.689 times Y, the Y variable, the response variable was height, so 10.7, divided by the X variable, the explanatory variable was foot length, 2.718. Do those calculations, boom, 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 and we get 2.71. That's the slope. The point is the mean of the X list, which is 24.77, comma the mean of the Y list, 171.27. So we've got a point and a slope. How do we write the equation? Well, y equals mx plus b. M is the slope. What's b? That's the y-intercept. Do we have that? No. So we have to find it, but we know an x-coordinate and a y-coordinate, so we plug those in. 171.27, that's a 2, equals 2.71 times 24.77 plus b. Solve for b, bada bing, bada boom, b is 104.12. Very good. So the equation of the line, and I could use y and x. I would have to make sure I've defined what y and x are. I don't believe that I've done that so far. So instead, I will use the words, which is perfectly fine. We are predicting the height. That's our response variable. So the predicted height, which we indicate by putting a hat over the height. A hat is just this sort of carrot-looking thing, this little peak over height. The predicted height equals the slope, 2.71, times the x variable, which is foot length, plus the y-intercept, 104.12. And that is a perfectly acceptable way to write the equation of the line. If you choose y and x, you need to put y hat equals 2.71, x plus 104.12, and you need to explain what y is and what x is, where y is the height in centimeters and x is the foot length in centimeters. Either one of those is an acceptable way to write the equation, but you need exactly one or the other. Finally, the residual plot. What is it? Well, the residual plot is a scatter plot of the residuals. The residuals in this case are on the y-axis. The foot length, which was our x variable before, is still on the x-axis. So we've taken the residuals for each of those 15 points and we've plotted them as heights above or below the x-axis. So positive residuals are above the x-axis, negative residuals are below the x-axis. So it's just a scatter plot of the residuals. Why do we care about it? Because it helps us to determine whether or not a linear model is appropriate for our data. So it could be that our data is best represented by something other than a linear model, a quadratic model, an exponential model, something like that. A residual plot helps us to determine that. So what do we want to see on the residual plot in order to affirm for ourselves that a linear model is appropriate? What we want to see is a random scatter of the points, that there is no discernible pattern between the points, and they are randomly scattered both above and below the x-axis. This is very nicely random. These points are randomly scattered Above and below the x-axis, there's no discernible point, there's no discernible pattern, there's no curve to this set of data. This is a beautiful residual plot, which tells us that our data is best represented by a linear model. So the line that we created is good for us to go forward with in making predictions about our data. And that's what it's really about. That's what linear regression is about, is to be able to make linear models that will allow us to make predictions for data points that we don't already have.